Hi guys, this is the last part of instruction level parallelism tutorial, and in this video we are going to talk about vector processors. In instruction level parallelism module we have talked about instruction level parallelism as a whole, loop unrolling, and how to implement instruction level parallelism at architectural level. For that, we have studied SIMD processors, array processors. Now, today, you are going to learn vector processors. So, for that purpose, what is the purpose of vector processor? Vector processor actually performs the arithmetic operation on the large array of integers or floating point numbers. Now, how vector processor do the operations? Vector processing operates on all the elements of the array in parallel, right? That means operation on different array elements will be done parallelly, but there is a condition. This parallel operation will be possible providing each pass is independent of the other. That means when loop can be unrolled and different iteration levels are independent of one another in the loop, as we have discussed in part 1 of this tutorial. If you still confused about how loop unrolling and instruction level parallelism works, just pause the video and go back to the first part of this video tutorial. So, you actually need computers that can solve mathematical for us, which include arithmetic operations on large array of integers or floating point numbers quickly. Okay, if you look into the real-time mathematical problems that a computer has to solve, in those scenarios, the size of the array might be in millions. In those cases, you need some general purpose computer which can complete those large mathematical operations in a short span of time. And that is the idea behind the development of vector processors. So, to avoid the overhead of processing loops and paths in the computation, some kind of parallelism must be introduced. So, this line actually tells about the idea behind the development of vector processor. Vector processing operates on the entire array in just one operation. That is, it operates on elements of the array in parallel. But can you perform any kind of operations in vector processors? No. Vector processing is possible only if the operation performed in parallel are independent. Just look at this figure. If you have a loop of 10 iterations, then in general processing procedure, or if I talk more technically, if you use a SISD processor, then at a particular iteration instance, ith instruction will be read and decoded. That means fetch the AI element and fetch the BI element will happen. Then AI and BI will be added if the operation is of addition type. Then you have to store the result in Ci, a third variable. Then you have to increment I and do the same thing once again in a different clock cycle until I becomes equal to 0. Now, the assumption is that you have a single segment in your CPU which can do this addition task. Now, suppose your processor is capable of doing 10 such additions parallel. Now, if you look into the operation, which is actually Ci equals to AI plus BI, as we have discussed while studying loop unrolling, these different instances of the iteration are independent of each other. That means the calculation of C0 is independent of the calculation of C1 and so on. So, if you have 10 such segments in your CPU which can add two elements parallelly, then you can fetch all the 10 elements of A and all the 10 elements of B in a single go, right? And in a single go, all the 10 additions will be completed and the results will be stored in different location of the C array. So this is the idea behind vector processor, which is primarily targeted towards arithmetic or logical type of operations. So here we have some technicalities of vector processor. The data for vector instruction are stored in vector registers. So vector registers are what? Vector registers are special type of registers which are actually targeted towards the storing of data for vector instructions. Each vector register is capable of storing several data elements at a time. This several data elements in a vector register is termed as vector operand. So, if you can recall the previous example, you can see that actually 10 instructions have been fetched in a single go. This instruction is actually vector type of instruction. So this instruction data related to this instruction will be stored into vector registers, as it is mentioned here. Each vector register is capable of storing several data elements at a time. This is the technical speciality of vector registers. Now, the several data elements in a vector register is termed as vector operand. So, if there are n number of elements in a vector operand, then n is the length of the vector, right? That means if you recall the previous example where we added 10 numbers in a single go parallelly, in that case the length of the vector was 10. Here is an example for your reference. Actually, supercomputers were evolved to deal with billions of floating point operations per second. Supercomputer optimizes numerical computation. Actually, as a general sense, the supercomputer name is suggestive that it is capable of doing a large amount of computation in a single short span of time. So, vector processors are actually implemented in supercomputers also. However, along with vector processing, supercomputers are also capable of doing scalar processing. Later, array processors were introduced, which particularly deals with vector processing, but they do not indulge in scalar processing. We have studied array processors before. Now, this was some technical details about vector processors. Now, what kind of computation can be performed with vector processors? And depending on that, you can classify the vector processors. If you look into the vector operand, each element in the vector operand is actually a scalar quantity, which can be either an integer or a floating point number. It might be a logical value or a character. Say, if you go back to the previous example, it was C0 equals to A0 plus B0 up to C9 equals to A9 plus B9. So, what here is being told, although you have 10 addition operations here, this 10 addition operations altogether is a single vector operation as per the definition of vector processor. So, the necessary data related to this single vector operation will be fetched into a single vector register at once. However, if you look at the individual operations which makes this vector operation, they are actually scalar quantities. As for example, the first element C0 equals to A0 plus B0, first instruction, sorry. Each and every element here is a scalar quantity, but when you look at the entire operation as a whole, it becomes a vector instruction. So, depending upon the nature of vector instructions, they can be classified into 4 types. What are they? Just look into the yellow table. First one is V mapped to V. Here V actually represents a vector operand, S represents a scalar operand. If you look into the operations, O1 and O2 operations are actually unary operations. O3 and O4 are binary operations. Why? Because in O1 and O2, here you have single operands. But if you look into O3 and O4, here you have 2 operands. They are binary operations. So, vector processes can be classified in these categories. That means where input is a vector, output is also a vector. That means if you map a vector to some other vector, then it is a vector to vector operation. Then a vector can be mapped to a scalar depending on the operation. As for example, if you try to find the norm of a vector, then input is a single vector, but when you calculate the norm or amplitude, then output is a scalar quantity. So this is an example of vector to scalar mapping. Then if you uh, try to find the cross product of two vectors, then output is again going to be a vector, right? Then in this operation, your inputs are two vectors and output is also a vector. Just a simple operation, say addition of two vectors. If you add two vectors, then what will be the nature of the output? Will it be a scalar quantity or will it be a vector quantity? Just think for a while. If you add two vectors, then output is again a vector. This is an example of this O3 operation. Then you can have an operation which involves a vector and a scalar, and output will be a vector. Example, if you multiply a vector, say v, with a scalar s, then the output also becomes a vector. So these are the types of vector operations which are actually possible. Now, what usually happens is most of the vector instructions are pipelined as vector instruction. Performs the same operation on different sets separately. This is as per the definition of vector operation. Most of the vector instructions are pipelined as vector instructions, perform the same operation on different data sets repeatedly. Now the pipeline has startup delay, as we all know, because there are some latches involved. So startup delay is obvious. So longer vectors would perform better here, because you don't have to start your vector processing over and over again. And depending on this, vector processors can be classified into two types based on from where the operand is being fetched for vector processing. In other words, for a processor to process some data, the data needs to be fetched into the processor from somewhere. It might be fetched from memory, it might be fetched from the registers, and depending upon from where the data are being fetched, two types of architectures were developed. First one is memory to memory architecture. In memory to memory architecture, what happens actually? Source, operands, intermediate and final results are retrieved, that means read, directly from the main memory, and in register to register architecture, operands and results are retrieved indirectly from the main memory through the use of large number of vector registers or scalar registers, right? That means in memory to memory architecture, you don't have any kind of intermediary. From main memory directly you go to the processor. But in register to register architecture, there are intermediary vector registers. Then you can think of this vector registers as if they are doing some kind of catching. So here are some examples for register to register architecture, and here you have some examples for memory to memory architecture. And here are some points to remember about memory to memory architecture and about register to register architecture. For memory to memory architecture, as main memory is involved, there is no limitation of size, obviously. Speed is comparatively slow in this architecture because each and every time you have to fetch something from outside memory. But in case of register to register architecture, it has limited size because you cannot bunch up infinite number of registers into your processor. Speed is going to be very high compared to memory architecture. And last but not the least, the hardware cost is going to be high in this architecture because the processor is going to be a little complicated. Now, look into the vector instruction format. When the processor fetches a vector instruction into vector register, the instruction has this format actually. It has an operation code. It has a base address source for source 1, base address for source 2, base address for the destination, and the vector length you need to specify. Just have a look into the definitions for this different segments of vector instruction. Operation code. Operation code indicates the operation that has to be performed in the given instruction. That means it indicates basically the type of the operation or operation that has to be performed. Base address. Base addresses actually refers to the memory location from where the operands are to be fetched and to where the results has to be stored. The base address is found in the memory reference instruction. So if you think it like an array, say this is an integer array, integer value requires 2 bytes to be stored into the memory. Now if this is an integer array and if this is your base address, now if you know the base address and vector length, that means how many elements are there into the vector, then you can surely calculate or surely find each and every element into this array. So this is the idea behind specifying the base address into a vector instruction. And lastly, vector length. Vector length actually specifies the number of elements in a vector operand. So as I have told before, once you know the base address of an array and number of elements, then you can access each and every element into the array. This is the idea behind specifying the vector length. Along with this, you need to specify the address increment. So if the address increment is not specified, then what will happen? Say you know the base address and number of elements. Fine. Now, if you don't know the address increment, say is the base address, then how can you get the second element? If A is base address and if this is an integer type of array, then along with A, if you add 2 bytes, it is going to give you the address for your second element. If you add more 2 bytes with this will give you the address for the third element and so on. So this value is basically your address increment. That means by how much you need to increment your base address to get the successive elements. Then you have an address offset. Address offset is always specified related to the base address. The effective memory address is calculated using the address offset. This is being used to find the physical address from logical address. So lastly, you have to study these two concepts called vector length and vector stride. This came out of basically from the problems which were faced while developing the vector processors. So why these problems occurred? Say, for example, you have 10 units in your processor to 4, 5, 6, 7, 8, 9 and 10. Yes, you have 10 units in your vector processor to perform the addition operations, right? Now your loop looks like, say, for I equals to 0, I less than 100, I plus plus, then AI equals to BI plus CI. Now, in this case, you have actually 100 addition operations which can be optimized using vector processors. But the problem is, although there are 100 operations, your vector processors has only 10 such segments which can do the addition task in a single go. Now, how you can optimize your problem? Very simple. Just send 10 elements in each go. How? Say, for the first pass, pass 1, we will send the vector instructions from A0 to A9, right? In pass 2, what you will do? You will send the instructions from A10 to A19 and so on. Now you see, if you follow this course in 10 clock cycles, this entire operation can be completed. But now where is the problem? The problem is that your compiler has to decide this number of passes. How many passes should be there depending upon the length of your vector registers. So what does it say? It says that for longer vectors, you can split the longer vector into multiple vectors of equal or of maximum plus smaller lengths, as we did in this example. We splitted a vector of length 100 to 10 vectors, each of length 10. And the process is called strip mining. The strip mine loop consists of a sequence of convoys. So here we have an example of strip mining. Uh, if you look into the first table, this is before vectorization. Here I has been initialized to 1, and then you have a do while loop which will run until I is less than equals to n. Then into the loop you are doing ai equals to bi plus ci. This is your original loop code, and then you are incrementing I by 1. Now the assumption is that for this particular example your vector has a length of 4, or your vector processor is capable of handling 4 operations parallelly. So you need to generate a code which can push a vector of length 4 in a single go to the processor. Just look at the vectorized code. Again you have initialized I to 1. Then into the do while loop, what you are doing, you are checking for I against n minus mod n 4. Why? Because in this case you are incrementing I by 4 rather than 1, and you are generating code which can add 4 successive numbers in a single go. If you explicitly write this code, it will look like ai equals to bi plus ci. I'll just paste them here. ai plus 1 equals to bi plus 1 plus ci plus 1. Then ai plus 2 equals to bi plus 2 plus ci plus 2. ai plus 3 equals to bi plus 3 plus ci plus 3. So in a single go you are calculating 4 AIs, right? Then you are incrementing I by 4. So this was an example of strict mining. Then lastly you have vector stride. What is the purpose of vector stride? In real-time calculation, sometimes you might need to consider some elements which are not adjacent to each other. Then vector stride actually represents the distance separating the elements in memory that will be adjacent in a vector register, right? Just this particular line can be a little bit complicated to you. For that, you have to look into this example. So, look into the two outer for loops. For I equals to 0, I less than 100, I plus plus, and for j you are doing the same thing. Then you are initializing aij, right? So, for the timing, say this is your I vector, I, you have 100 elements here, and then you have j vector, you have 100 elements here. So, sorry. Then you are calculating aij. So, aij is essentially a two-dimensional matrix, right? So, aij is a 100 by 100 matrix. Hundred by 100 matrix, right? Then you have an inner loop into the core segment. It is aij equals to aij plus bik multiplied with ckj, right? So what happens here is that if you look into this matrix, it is actually not accessing the adjacent elements. Just follow me and give it a thought. This C actually is not accessing the adjacent elements in memory, right? Have you been able to figure out why this happens? Let me see into this. Say this is your C matrix. In C matrix, once again, you have 100 rows and 100 columns. So you have 100 rows and 100 columns. This is your C matrix. So if you look into the loop variable for C, it is specified by K and J. That means row index is K and column index is J. So what actually happens here is that while k equals to 0 and j equals to 0, so just look carefully into the matrix, which element you are going to access. You are going to access actually this element. For this element you have k equals to 0, j equals to 0, right? Now, as k is being incremented into this inner loop, for j equals to 0 into the next iteration, the value of k will be 1. So, during the next iteration of this inner loop, you are going to access this element for which k is 1. So, although in your calculation you are using this c variable in back-to-back iterations, but in memory these two elements are 100 locations apart because number of columns in your matrix is 100, right? So this is actually your stride distance, which actually specifies the distance among the elements which you need to punch in a single vector instructions, or in simple terms, in other terms, when you push this instruction set into vector register, these two elements has to be sent to the vector register back to back, one after another. But in memory, if you see, they are not adjacent, they are 100 elements apart. So this is vector stride which solve this problem, where the memory elements are not adjacent for a vector operation, but the elements will be necessary to be punched into a single vector instruction. So give it a thought, take your time. This was all about vector processors. Now, how you need to study this material? First, read the material, then watch the video, then once again read the material in between the lines, take notes wherever you think necessary, and give it your thought. Take your time. Thank you.